All right, let's talk a little bit about physics in this chapter. We're looking at derivatives as rates of change, and so it doesn't have to necessarily be physics. Anytime that something changes, you can take a derivative and measure the rate of change. Like it could be money in a bank, it could be the growth rate of trees, it could be really anything. But oftentimes, uh, and especially if you take a physics class, you'll see it a lot in physics. So let's uh, let's write out real fast. So the position of a falling object at time t, you can use this equation, 1/2 gt squared, where g is a gravitational constant, plus v naught of t. Now v naught is your initial velocity. So like let's say you throw it up in the air, it's going to have an initial velocity that it starts with. So v naught times t plus S naught, or S naught's your initial position. So that's if you throw it, in the air from 10 feet off the ground, then you have to take that into account as well. This G, this gravitational constant, actually, it can be a couple of different things. It's gonna be negative because remember gravity's pulling it down to the ground. But if you're doing feet, you're gonna have feet per second squared. If you're doing meters, 9.8 meters per second squared. Oh, that's looking a little fuzzy. Let's do that. All right. So now, if you take the derivative of the position, then you're going to get the velocity. All right. So your velocity of t, well, that's just s prime of t. That's just the derivative. So that's going to be how fast is it moving at any particular time. Well, if you took the derivative of this, you're just going to get 2 times a half, so that's just 1. So you're going to get g times t, so your gravitational constant times t, plus v naught of t, the derivative of that is just going to be v naught, and then your s naught, it doesn't have a t on it, so that's just going to go away. And now if you take the second derivative of the position, you get your acceleration at time t. So that equals s double prime of t. So the derivative of this, well, the derivative of g of t is just going to be g. And, that really makes sense intuitively because this is your gravitational, like the acceleration of gravity, acceleration of a body due to gravity. So that part kind of makes sense. That one's going to be constant and not change. So let's take a look at how you might use this in a real quick example. So let's say we'll use a diver. So you have a diver jumps from, and let's use feet per second. So we'll call it, we'll say you're 32 feet up. We'll try to keep everything, the math kind of easy on this one. So from 32 feet, and has an initial velocity. Velocity, is that still on the screen? Yep. Let's see. How about we'll do 16. All right, so let's go ahead and model this, and then we'll look at a few equations that we can use to to find some interesting stuff out about this. So let's go ahead and plug this into our s of t equation. So we'll go ahead and write it out. So 1/2 g, we'll use feet. So 1/2 negative 32 t squared plus your initial velocity is 16t, and how high? He's 32 feet above. So this will give the position at any time t of this diver. So the first question that I want to ask is, well, how long is the diver going to be in the air? All right, so maybe how long until the diver hits water. All right, well, in this case, we don't really have to do much in terms of derivatives or anything like that. We just really have to set this equal to 0, because when this equals 0, that means his position above the ground is 0, like he's on the ground, or in the water in this case. So let's simplify this to negative 16 t squared plus 16t plus, and these t's kind of look like pluses, so sort of keep that in mind, equals 0. All right, so let's go ahead and solve this. Let's bring this 16t over here. So we're going to add 16t squared. All right, so let's I'll just kind of draw a big arrow. So we've got 16t squared equals 16t plus 32. So let's go ahead and divide all these 16s out of here. So that's going to cancel. That's going to cancel. So we're left with t squared equals, this is going to be 2, t plus 2. And this equation is sort of easy enough that we can just kind of look at this, and we know that t equals 2. Because 2 squared is 4, 2 plus 2 is 4. So not a lot, not very difficult math there. All right, so how long before the diver hits the water? Well, he's going to hit the water at 2 seconds, which, you know, that's a pretty good length when you're in the air. All right, so the second question we can ask, or that we can answer with this, is how fast is he going? Well, that's a good question. With this, we just take the derivative, because remember, the first derivative of the position, let me scroll back up here. The first derivative of the position gives us the velocity. So we already sort of did the math up there. We got our equation. So the velocity at t, let me write it right here. So that's going to equal g times t plus v naught. All right. Well, let's go ahead and throw this in, the things that we know. So this equals negative 32 times 2 plus, what was our v naught, 16? All right, so we get out our handy dandy calculator. All right, so we've got negative 32 times 2 plus 16, so that equals negative 48. So all that we did, and that's in feet per second. So all that we did is we just took we had our time t, and we took the derivative of this position equation to get our velocity equation. All right, so that's pretty straightforward. Let's look at one more thing. Let's say, well, what's the maximum height? All right, well, that's a good question. Good question to know. So max height. Hope I spelled that right. That doesn't look right to me. Apologize if my spelling's a little bit off. All right, so what's the maximum height going to be? Well, all right, we've got our, first off, we got to figure out when is our velocity equal to 0. Because if you think about it, let's say this is our curve right here. He's going to jump, whoop, and then start coming back down. So at some point, he's going to reach that weightless state. Right? When there's nothing, he's just kind of sitting up there in the air before he starts coming down. So we've got to figure out, well, at what point does that happen? Now, we can do that because, or we can figure that out fairly easily. So we already have our velocity equation. So we have to figure out, well, at what point is the velocity equal to 0? Okay, so we got to figure out the time first. So our velocity equation equals negative 32 times t plus 16. And we've got to set this equal to 0. Alright, so this is pretty easy to solve. We're just going to bring the 32 to the other side of the equation, so we're adding 32 to each side. So we've got 32 times t equals 16. So we can just kind of look at this one, and we know that if I divide each side by 32, I know that at time t equals 1/2, that my velocity, whoops, you can't see that, and we're about at the bottom of the page here. I'll get another one here in a second. So at time t equals 1/2, my velocity is going to equal 0 because we set our velocity equation to equal 0. So all that we have to find out then, since we know what this is, we have to plug it back into our position equation. And if we plug it into our position equation, we can figure out what height above the water is going to be the max height. So let me go ahead and flip this over so that, here we go. Okay, so we have t equals 1/2 a second, and my position at time t equals 1/2 times negative 32 times 0.5 squared plus 16 times 0.5 plus 32. So this will give me the maximum height. So we'll get our calculator out again. So we've got negative 16 times, let me do some parentheses, negative 16 times 0.5 squared plus 16 times 0.5 plus 32. So we see here that we have a maximum height of 36 feet above the water. Alright, so kind of a neat way. First you find the derivative of it and you set it equal to 0. That gives you the time. Then you use that time to go ahead and calculate what the position is, at that maximum. Alright, so real quick, let me just sort of show you another kind of thing that you can do. It's neat to see these things graphed out. So I'm just going to say y equals, I'll simplify it, x negative 16. 16 is just 32 divided by 2. So there you have that, plus 16x plus 32. Now let me move this. Now we can see here is our curve. You can see we jumped off of the diving board at 32 feet. So we jumped off right there. We hit our maximum. This looks like at 0.5. Zoom in. Oh, it's not going to go. Well, I'm fairly certain of our math. Shows we had a maximum at half a second, 0.5. And you go over here, and that looks like 36 feet to me. So you hit your maximum at 36 feet. And then coming down here, we see you hit the water at 2 seconds. So this is your seconds. Down here, this is your height over here. So the math kind of checks out. This is a nice quick way if you want to sort of avoid doing all the derivatives and stuff. You can just plug it into here, and as long as it's a lot of times the derivatives will be more precise because that'll let you know for sure. But this is kind of a neat way so that you can see it modeled here. So that should get you going on derivatives with rates of change. Remember, it's not just limited to physics. There's really anything that has a rate of change. You can use this. You can find a derivative to figure out how much it's changing. There's just a whole lot of information that you can find out once you start taking derivatives of stuff.